Okay, this is open to anyone who wishes to come up and scribble on the whiteboard. Ask a question, correct me, point out something I didn't know, whatever. This is basically, I'm assuming that I am in a room full of peers who all have different knowledge. And, well, I hope we all learn something. About 4 months ago, I started trying to implement CCW, the CCW algorithm. And I went through about a dozen iterations of the algorithm and wasn't happy. In other words, I look at it and go, nah, that's got issues. So I decided to go back to square one, the noise level. So that's where I want to start. Square two. Yeah, sure. We saved it for you. All right. I do need to learn to write again. Okay, the traditional view of CCW is you integrate over the DIT interval. And you have the DITs, you've synchronized the sender and the receiver. And, well, that actually corresponds to picking some point here, this threshold. So this is the probability distribution function for the QRM.
I was going to ask you if you could label the axes.
Oh, well, it's, I don't know what the magnitude of the QRM is.
Is it arbitrary?
Yeah, I mean, my concept is what you do is you listen on frequency for 10 or 20 seconds, you make an estimate of the QRM, and then what you do is you pick some point out here where you have a high probability that you have a signal. Now there's an issue with CCW. If you have an integration over this, you're home free. But if you have an integration over this, you've got a problem. If these two have equal magnitude, when you decode it based only on the magnitude of the integration, and I'm substituting the average value because it's the integration divided by the number of samples. So here's the thing, is the standard deviation of this and this is over in here. The standard deviation of this is over here. It's a much larger standard deviation. So basically the idea is to use two metrics for CCW, not one, to basically require that the signal be above some level here, which I will get to later, and below some level here, like preferably back in here, that says that, okay, this signal, type of signal, not this type of signal. Because if otherwise, if you decode this instead of A, you get D. Not very satisfactory. And so the thing is that the difference in the standard deviation will allow you to discriminate against that. So when you decode it, whereas, if you don't use the standard deviation, you're going to decode this as or wait, no, that's you. Sorry. I am still trying to relearn Morse code from when I was last licensed in 1980. My first license was in '68. So the thing is that what we want to do is we want this answer, not that. Everybody follow the logic? I really need my sheets back. Since that was my cue. Yeah, hand it now. Because they're out. Yeah. Okay. Everybody's got one. Okay. So basically I kind of short-circuited the first four things, the first half of the page. But basically what I am proposing is that one use for detection the requirement that the mean value in a DIT frame or a DA frame is equal to alpha times the standard deviation of the noise plus the mean value of the noise. So in other words, that's just saying we want to be here somewhere. And we can adjust alpha to whatever we want. That's approximately what current CCW procedure is, except that it's really more, X bar greater than alpha, but we don't bring into it the standard deviation. So we just pick some arbitrary point here without paying any attention to the distribution of the noise. And then also require that that the standard deviation of, well, no, I'm sorry, that's wrong. X bar, well, actually I should write it like that. The average value of the signal in the DIT interval is above some certain level, and then the standard deviation of, no, it's not, I'm sorry. It's, well, it's either, there's a divide by n difference between this and the, sum of X bar. So the idea is then that you require that be less than the standard deviation of the noise, so that, plus the mean mean value of the noise. So you pick some point out here and you say, if it's this side of the distribution, it's not a noise spike, it's a real signal. And if it's out here, it's probably a noise spike. Now I can't tell you what, and there's a beta here. I can't tell you what those values are. Those will have to be determined by.
And what you're describing is for a non-coherent detection, right?
I'm describing the noise. I'm describing the characteristic of QRN.
Oh, you're just describing the noise.
I'm just describing the noise. And what I'm trying to do is I'm trying to set forth criteria that will allow you to say, that's noise, that's not noise. At very, very, very low power levels. As I noted earlier, my goal is 100 milliwatts or significantly less, all the way to Australia, reliably, 100% reliably, for 2 kilobytes. I mean, we're talking not a lot of data, but hertz of variation. So you can't detect a tenth of a hertz variation as some ionospheric level goes up and down. Relevant to trying to figure out the effect of the clips and stuff like that. So then, okay, now we get to the messy stuff. Okay. So, this is for everyone who has suffered through a ridiculous amount of mathematics. Fairly simple. This is a spike. It's a Dirac delta function. It has infinite amplitude, infinitesimal width, and an area of 1. And if you shift it by a time tau, then the difference of these two is this has got a real part, which is constant, and an imaginary part, which is 0, or very near 0. You've got round-off error when you do the FFT. In this case, you have the situation that the imaginary part and the real part have a phase difference. A lot of the CCW stuff that I've read talks about, try this offset, this offset, this offset, this offset, this offset. There's no, first of all, it's not accurate. Secondly, it's computationally a lot more trouble. All you have to do is take this, okay, by the way, okay. Pictorial notation, time, frequency. This is my thing for a Fourier transform. So the thing is, what you do if you want to determine tau is you do a linear, you transform to frequency, both signals, both your sync signal coming in and your internal clock. and then you multiply them together. When you multiply them together, you will get this linear phase shift. And you just do a real simple L2 regression, least squares regression, and bam, you have got the delay time to within a fraction of a sample interval. So this is, and when I was in grad school at UT Austin, okay, one of my colleagues took 4 millisecond, 24 channel seismic data, and he measured the time delay between each of the samples produced by the multiplexer and came out with 83 microseconds. So in other words, each adjacent sample in this 24 sensor array is different by 83 microseconds. And for his dissertation, he had to correct for that. And, you know, so it's extremely powerful because, you know, it's like 1/24 of 4 milliseconds. And you can do this, you know, very readily. I mean, it is computationally very inexpensive. Okay. In seismic, we refer to that as a boxcar. Looks like a dock. Well, here's the deal. Is that, we call that a dip. It's got a really narrow sine x over x sync function. If we make it longer, oh, I'm sorry, I got that, that's completely backwards. The short one has a really broad spectrum. That's why it sounds like a dit. The longer one has a much narrower spectrum, and so it shows up like that, and it's a dot. Because this is DC here. So, you know, it's low frequency, and this is what we hear. There's nothing I'm telling you that you haven't heard with your ears. So, the point here is that whatever is wide in one domain is narrow in the other domain. And it doesn't matter which way you go, all the transforms are symmetric. So you can take the frequency domain representation, call it the time domain representation, and the time domain representation is now the frequency domain representation. So,
I have a little bit of point of confusion. When you're talking about the boxcar, the dip, or the dock, are you talking about a DC level like you would see on an oscilloscope? Because what really happens is that the carrier's turned on for that length of time.
yes.
And that
yes.
carrier's at a much different frequency. So what detection are you talking about here?
Well,
where
okay,
you can apply
okay.
that?
I've, as was stated, this is like an octahedron. I spent weeks trying to figure out what order to try and present this. You know, and I promise you, I probably have it
Well,
wrong.
you talked about being able to hear this.
Okay.
And that, to me,
Right. So
sounded like a tone.
so let's say that we have a sinusoid, and we multiply it by a dit. In other words, it's the sinusoid is running. We turn it on. We turn it off. Okay. that's going to produce this narrow thing like that. And that is going to have a spectrum which is a sync function, excuse my, centered on the side tone frequency, or the BFO frequency, the reception frequency. And so does that answer your question correctly, properly?
Yeah, I guess I was just getting confused about, so it would look the same as if it were a square wave then.
Yeah, well, that's
The spectrum might look a little different, more
well,
side
the
tones.
thing is, it will be a square. It will be the spectrum of a square wave, but because it's multiplied by a sine wave, the center frequency of the sync function will be the frequency of the sinusoid.
Okay.
And so, our ears are wonderfully sensitive to tit and da. A da is 3 times as long as a dit. And so the spectral width at audio is 3 times as wide. Our brains are really good.
Yeah.
So, Rachel, let me ask you more directly. You have about 10 minutes. You plug your analog to digital converter into the audio output of a receiver that's listening to a CW station. What's the computation that will result in accurate Morse code coming back out the other end of the computer?
Oh, it's basically well, the n is not quite. No, actually, the n is, so it's just the average value of the sum of all the samples.
But isn't that 0? Isn't it going to be a DC of 0? Because it's going to be crossing the 0 axis. And if you take an average, it's going to average out to 0, right?
Our ears are not sensitive to phase. Therefore, we hear the absolute value of the noise. We don't hear if it's positive or negative. We can't tell that.
But I think I'm just saying what he was asking, like an ADC, if you take the data coming out of an ADC, it's not our ears, that sum of X is gonna be 0, I think.
No,
Because
that's why the absolute value.
Oh, okay. So it's not you're taking the sum and then absolute value. You're taking the absolute. So you're getting
I'm
twice.
summing the absolute value.
You're
Yes.
getting twice the frequency then.
Well, no, it's not. It's not twice the frequency. It's just that there's no cancellation.
Yeah, because the bottom going piece, you're gonna if you take the absolute value, it's gonna come up. So you're gonna get twice
It's
as
all
many.
like,
bits.
it's like running it through a rectifier.
Yeah.
All right, so that's your statistical metric. How do you know when to begin the sampling? How do you know when to end it? And what do you do to make a decision whether there was signal in that time period? I mean, that's really the question of coherent CW.
That is indeed. Unfortunately, okay. I didn't organize it in this fashion in the handout, but I will. There's no reason at all for me not to change the order in response to questions, because this is exactly what I wanted to do. Is I wanted to discuss this with people who understood a lot of this stuff and would ask the good questions. So, if you will repeat your question. I'm sorry, I was racing.
I think he was asking. I
Oh,
don't
it's the
mean to be asking
synchronization.
this question for him.
Okay.
He was asking, how do you detect And how do you know the threshold at which to say that's a dit or that's a dot?
Oh, well, that's the part about the standard deviation. Okay, the synchronization is a whole different problem. Okay, a commonly proposed, and I had actually initially started out with the idea of using error, HH, 8 dits, as a synchronization code. That's got a problem. The autocorrelation of this is a series of triangles, which I'm not drawing very well. Noise-free case, it's really easy to pick this point. You throw a bunch of noise in there, and it starts getting smeared out, and now you don't know exactly where the where's the zero. In the 50s, when they were developing spread spectrum, direct sequenced spread spectrum, a man named Gold came up with what are called gold codes. These are pseudo-random sequences which have the property that a autocorrelation of the signal and the expected signal has a very narrow spike, and any other series basically are zero.
For a pure frequency, for a pure tone, like a pure frequency, yeah.
No, well, no, it's just, the thing is, in other words, what you get, okay, this goes down to actually the bottom of the backside of the second page. Okay. If you have a Gaussian random sequence A, and you have another Gaussian sequence B, okay, if you autocorrelate these, and I normally notate this in the frequency domain where it's a multiplication. So the autocorrelation of this is phi A. The autocorrelation of this is phi B. Now, convolution flips the series. Autocorrelation doesn't flip the series, so it's the complex conjugate. And it slides by, and when it perfectly matches, you get a spike.
Right.
And if it doesn't match, you get nothing. So the thing is, whoops, no, that's not the way to write that. Okay, so if you autocorrelate that, it's going to go whoop. You autocorrelate that, it's going to go whoop. But if you cross-correlate the two, so you get something, except that, so this is phi A, this is, well, actually, it's phi A, it's phi complex conjugate. It's phi A complex conjugate A. So play around with the imaginary part. And same thing for this. But if you have A and B autocorrelated, and they have good correlation properties, i.e. they're highly uncorrelated, then what you get back is you get back basically nothing. You know, it's intrinsic, you know, if it's long enough, it's zero. And so the thing is that by picking something that has this kind of a property. What happens with a lot of pseudo-random sequences is you wind up with a bunch of junk.
Rachel, what you said to me in emails was really that you had solved coherent CW. So what's the solution? How do you get your framing, and how do you make your decision at the end of the sampling time?
Well, what you do is you use a gold code.
Reg, I'm going to stop you. You can't, because that's not Morse code. It's outside of regulation. It's not useful in amateur radio circuits.
You can pick a set of dits and dots.
Okay, that's fine, but you can't use something that's outside of A1 telegraphy as defined by the International Telecommunications Union.
Well, okay, my understanding of the FCC regulations is that as long as the protocol is published.
That's not A1 modulation anymore. That's not what technicians can use on 80, 40, and 15 meters. That's digital communication. It's different from A1 on-off telegraphy for oral transcription.
Well, it's still on-off telegraphy.
But it's not meant for oral transcription. It's not a previously published code. It's not ITU Morse. So you can't. So just don't use that. Use something else. Really. But show us how, you have 5 minutes. Show us how you've solved coherent CW.
What?
Show us how coherent CW works.
Well, I mean, coherent CW works by looking at the magnitude of a bit frame relative to the background noise.
Okay, how do you find it?
You measure the background noise, you pick a point that's several standard deviations. I mean, if you go 3 standard deviations, if you've got a signal that's 3 standard deviations away from the mean value of the noise, there's a 99% probability that's a valid signal.
Okay, so once again, you have plugged your AD converter into the speaker output of the receiver. You have a digital converted stream. What do you do with it? What's your algorithm? What's your code?
Well, okay, I'm not sure.
He's asking the algorithm. What's the algorithm you use? You get the ADC data coming in. What do you do with it to figure it out?
Basically, after you have with a suitable sequence, and you can pick some series of characters. I mean, there's no reason.
Go ahead, keep going.
Okay, so once you get the synchronization, then you just simply compute the mean value and the standard deviation when there's no signal present, and that becomes your criteria.
But how do you know? This is what I was saying before. How do you know that there's no signal present? Because if you go and you measure it, there could be a signal present. Is there some kind of? And I think that's.
Oh, I'm assuming you're listening.
What happened? Is there some kind of synchronization between receiver and sender? Like, how do you know when to start? When there's noise?
The whole thing is the autocorrelation. Is what you wanted, the autocorrelation.
That's using to say, okay, I've got a frequency, start. Like if you do your autocorrelation, it's telling it's like a Gertzel algorithm.
The autocorrelation
is telling you that there's a frequency present.
When I Fourier transform the autocorrelation, I wind up with a real part and an imaginary part. And you compute you do a linear regression on I omega tau, and you solve for tau. And now you have precisely to a fraction of a sample period of the ADC, you have the delay. my point about 4 millisecond ADC data being, resolvable to 83 microseconds.
No, got it, yeah.
Okay.
Does the process presume that you know something about the duration of the baud rate of the CW?
Yes.
Okay,
Yes. No. Yes.
You know precisely what the baud rate of the CW is supposed to be? And does it also presume that you know frequency, or not necessarily?
No, you have to know the frequency. Basically, what CCW is it's a two-dimensional filter. It's frequency and it's time, and it's synchronization of the time. So you're filtering over two dimensions. You picked a frequency, and now you've aligned your transmission timing
By dithering that.
so they match at the sender and receiver point. And and this is like a 2x2. It's a little more than a 2x2 matrix inversion. But doing a linear regression is not very difficult. And as soon as you solve for tau, you know how much to move the frame in order to be perfectly aligned. Now, all of the stuff that I've seen, nobody mentions that, well, gee, if I receive W and I decode it properly, I can do a cross correlation on W at the clock rate of the receiver against the received signal. And so you can resynchronize the reception, like in other words, every nth character. You do the Fourier transforms, you do the linear fit, and you update the start and stop time of the dip frame.
So signals that are not at the specified rate show up as more noise?
Yeah. I mean, I personally, 12 words per minute is painfully slow to me. And if you go to 16 words per minute, 75 millisecond dip frame instead of 10, you're up to 16 words per minute. And if you go to 50 milliseconds, you're at 24 words per minute. Now, everything is based on time times power times bandwidth. And as long as that equals a suitable value that you can detect, you can vary any one of those three, so long as the product is the same. QRSS makes this very large, and this very small. So you're getting a trade-off, and it works. It's perfectly valid. But that's what the effective signal is at the receiving station. So the other thing that I wanted to bring up is the whole idea of spread spectrum. Okay, we currently do CW at the narrowest bandwidth we can manage. I mean, it's basically the transmit frequency and the modulation rate. So it's narrow. So this number is small. Now let's suppose that we have a PRN that's known. And we modulate it at a kilohertz. So we spread the signal out over a kilohertz, and then we turn it on and off. Well, now we've got more bandwidth if we've got good properties of the autocorrelation. We can pick stuff out of noise. You get processing gain. But processing gain is basically the modulation rate divided by the data rate. GPS, by design, the signal at the antenna is 54 dB below the noise floor of the receiver. But they've spread the signal out over about a megahertz, and so they get 60 dB of processing gain. That's enough to decode it. And so, that's, aside from the use the standard deviation to augment the CCW decoder. Because CCW it's a nonlinear decoder. We're not listening, it's eliminating the shh by ignoring it and just going beep, beep. So you're listening to a noise-free signal, which is, at low power is just a hell of a lot easier on your head.
So theoretically, what kind of signal noise, apparent signal noise increase can you get using this technique?
Oh, well, it's basically, as I said, it's the modulation rate divided by the data rate. So if you've got a modulation rate of 1,000 bits per second, and you've got a data rate of 1 bit per second, you now have 30 dB of gain. And that's what makes this is actually an accidental. When I was trying to prepare this, I was going down and all of a sudden I went, oh, wait a minute. Well, why can't you spread out the spectrum and lower the power level? Because I want to do 10 to 100 milliwatts all the way to Australia, reliably. And which means that it's limited to, if you're going to do it at that power level, it's limited to, I figure, a couple of kilobytes. What I generally assume is a couple of kilobytes a day. In other words, basically a direct email point to point on HF from one person to another person. And so, I'm grasping at, okay, well, what are our options for doing this? And this is one, it's sort of related to CCW, except, well, you still have to have the timing. because you've got to identify the PRN, and you can't afford to do Fourier transform, linear regression, and recalculate the phase well, you probably could if you have a Raspberry Pi for the processor, but in general you can't afford that. So
Well, you need to do some of that so that you know if something happened.
well, no. The thing is, in other words, what you've got to do is in that case, what you do is you just synchronize on a string of dits with the PRN, and that will do it quite well. And it's just a question of, the longer you make the sync signal, the lower the power can be.
Something here. Oh, I couldn't possibly.
The thing is,
It's way over my skill set,
but
but I can see intuitively that there is a similarity between spread spectrum techniques and the technique of using CCW.
and QRSS. QRSS is just really slow CCW,
Well, that's
minus some of the synchronization.
QRSS is just averaging though, right? Non-synchronous averaging,
Right,
right?
right. It's
That's usually done visually with.
right. It's
Right.
minus the synchronization part.
Right.
But the thing is that you can certainly do it synchronously, and you'll get gain.
I
from
think it
that.
could be fun if people could come to an agreement about the protocol. I think it'd be
Oh,
fun.
the thing is, as I say, I started out to write software for this and didn't like the algorithms that I was coming up with. And so my bucket list item is to implement all this stuff as freely available software for Ashar to put in the ZBitX and
Now, if you did this with a standard Morse, and let's say you agreed to a rate of 16 words per minute, as you said, then if the signal were above the threshold, I could still copy it by ear.
not if the DIT is a good imitation of random noise, you might be able to hear it as shh, 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 shh.
Huh.
But that's all. Whereas if you do the computer processing in an SDR, you get dit, da. In other words, you get a clear tone from the side tone with no noise, because you're not actually listening to the incoming signal, you're listening to the processed signal. And as I think it's George Heron observed, it's like an octahedron. You look at it, drove me nuts for weeks trying to figure out where to start, because you kind of have to know all of it to understand the first part, because it keeps kind of going in these weird circles.
Oh, I'm sure.
It's
sure.
It's actually easier to do than it is to get your head around the first time that you see it, because it's a combination of a bunch of stuff that's relatively obscure. I mean, I don't know of any, other than, the, 1950s super secret spread spectrum stuff, which is either direct sequence or frequency hopping.
Yeah.
I don't know of anything else that does this. Well, with one exception, there actually is, this is used in seismic, where on land, they will run vibrators.
Oh, yeah.
And they will do different patterns on the vibrators so that they can record multiple vibrators at different locations into the same geophones and not interfere with each other.
It sounds like exactly the same thing, just slowed down a whole bunch.
Yeah, I mean, it is, we've all seen this stuff before in various forms. It's just not always been obvious.
Well, I think the reason CCW it could appeal to hams is not if you made it into another digital mode.
Oh,
But if by doing so, they could, like RTTY, they could communicate in real time.
yes. I mean, I want to do this with a hand key.
Yeah, right.
I'm fully with the keyboard.
It's an interesting, it's been around a while.
The thing
But,
is,
the analog process for this, though well documented, never caught on because
it was too hard.
It was such a tiny little niche of ham radio.
Well, and the thing is that physically, the circuits that you had to build to do it at all
right.
were
Cumbersome.
were cumbersome and very prone to not staying in alignment
Yeah.
because of component tolerances and
Yeah.
drift and all of that. And so what I'm trying to do is codify this in a fashion and document it in the form of source code. And then just, see what happens.
Create a library for CCW.
That was what this all started with. And
I appreciate what you're doing.
and the thing is, I wanted to meet Hans Summers so badly
Oh,
that I coughed up the money to come here. And
his equipment is it's designed for this and other
the
modes.
thing is,
mean,
I was designing a radio.
he's not doing it, but
No, I was
Some-
designing a
somebody
radio
do.
for
Yeah.
this
Yeah,
based
that would
on
be
the micro SDR, true SDR.
have you talked to Hans about it?
Oh God, yes.
Oh, okay.
Oh,
Okay.
and
It'll happen then.
Hans
What was
is
your name again?
Reg Beardsley.
Okay.
I'm not.
Nice to meet you.
I'm not.
Thank you for this.
I'm not licensed. I've been licensed twice, but at age 36, in college, I let my second novice license lapse because I couldn't afford a radio. I was so freaking poor.
We get so many people come back to ham radio when they retire.
Yeah. Well, I mean, the thing is, the wonderful thing about Hans is he's making radios you can afford,
Yeah, yeah,
as is Ashar.
yeah.
And the thing is that, it's, I find it very frustrating that you can't, up until recently, you couldn't do serious work in amateur radio. Back when I was in grad school at Austin, I was very active, and I had a 5 megahertz recurrent sweep IO18 Heathkit scope. And I had a DMM, and I had a volt ohm meter, and I had some signal generators I'd made out of 555s and 741s and stuff, and that was it. And I started building a direct conversion 40 meter transceiver.
You started building what?
What?
You started building what?
A 40 meter,
Oh,
transceiver project. Basically, following, solid state design for the radio amateur.
Yeah.
And it didn't work.
It didn't work.
Well, I had a strong suspicion that the problem was I wasn't on frequency, because I had no way of measuring capacitance or inductance. I didn't have a nano VNA or the $20 LCR tester. So there just wasn't. I was basically just. I still have them. I actually later got 8601 sweeper, and sure enough, I was absolutely dead right. I was tuned between about 6.8 and 6.9 megahertz, which really doesn't pick up much of anything.
Well, another aspect of this, talking about people that might not have the means for an elaborate antenna system or elaborate gear or power, is for something like this, you don't need a lot of power.
No, that's
100 milliwatts is plenty. And if you have a watt, well, then you can have an antenna that's 10 dB down.
Yeah, no, there's
Which means not much of an antenna.
there's a tremendous amount of potential in it. There's a whole pile of work to be done on it. But, this has been a 40-year obsession of mine, because I worked 9 months as a seismic processor and 9 months as a seismic interpreter before I got my first and only 2-week training course in digital signal processing. I'd been promised months in Tulsa, living in a hotel room, being trained, and I got none of it. And so I had to, evenings and weekends, I took my stack of 4 books and I just went through them, and each time I went through, there was a little more I understood, and eventually I figured out how to do it, but I got hooked on it. It was like, oh, you can do such cool stuff. And
well, I hope you publish it through Archive or somebody so that we can
I know.
Put it on the web. I'd be thrilled to see it.
My intent is to make this, widely available, because the thing is that we are facing uncertain times. I think most of us recognize that. And the ability to reliably communicate with someone at distance without any of the other infrastructure in place is likely to become critical.
It could happen.
I hope I'm dead by then, but
I probably will be.
I turned 71
Thank you,
on
guys.
Tuesday. Anyway.
It's above my head.
I was kind of terrified of this, because it's like, okay, how do you go in an audience you don't even know which is made up of electrical engineers, English majors, music majors, God only knows what. How do you go into, all this integral transform stuff?